This video is sponsored by Squarespace. Scientists have recently confirmed that Earth was struck by a mysterious and highly energetic cosmic ray particle. This tiny single particle carried an astonishing energy of over 240 exa-electronvolts, equivalent to the kinetic energy of a high-speed baseball or the impact of dropping a lead brick on your toes from waist height. This may not sound remarkable, but think about it. All that energy is confined into a region smaller than an atom. This level of energy is about 1,000,000 times greater than what our most advanced particle accelerators can produce. Named Amaterasu after the Japanese sun goddess, this particle is the second most energetic cosmic ray particle recorded to have struck our planet. The most energetic remains the Oh My God particle, detected in 1991, which boasted an energy of 320 exa-electronvolts. But here's where it gets interesting. When scientists traced its trajectory to its source, they found that nothing in that region of the sky could produce such a particle. Dubbed sometimes as the Oh My Goddess particle, Amaterasu seems to have originated from a mysterious, seemingly empty region called the local void. Additionally, similar to the Oh My God particle from 1991, Amaterasu has broken the theoretical energy limit proposed for cosmic ray particles traveling over certain distances in the universe. This means there's an extremely powerful object nearby, or an unknown mechanism that has produced this particle. But what are cosmic rays, and what are they made of? How did scientists detect Amaterasu in the first place? Finally, and most importantly, why is detecting this particle such a significant breakthrough in physics and astronomy? Cosmic rays are high-energy particles from outer space. Their discovery dates back to 1912 when Austrian physicist Victor Hess, using high-altitude balloon experiments, detected increased ionization levels in the atmosphere. This breakthrough suggested the presence of penetrating radiation from outer space, contradicting the then prevailing belief that radiation was solely an earthly phenomenon. These cosmic rays are primarily composed of protons, which constitute about 90% of the total, along with about 9% alpha particles, or the helium nuclei, and a small fraction of heavier nuclei and electrons. Cosmic rays have various sources. Some are emitted by the sun, especially during periods of intense solar activity, like solar flares and coronal mass ejections. More energetic and far-reaching are the galactic cosmic rays, believed to originate from supernova remnants, pulsars, and possibly the surroundings of black holes within our galaxy. Additionally, there are extragalactic cosmic rays that may come from even more distant and powerful sources in the universe, such as quasars and active galactic nuclei. These rays vary in energy, spanning from 1,000,000 electrovolts to over 50 exa-electronvolts, with the latter known as extreme energy cosmic rays. So far, only two particles have been found to exceed an energy of 200 exa-electronvolts, the Oh My God particle and the Amaterasu particle, and both of them have left astrophysicists puzzled. But how were these particles detected in the first place, and what's their source of origin? Before answering that, let me introduce you to the sponsor of this video, Squarespace. If you are someone who has no coding experience or software knowledge, but still wants to establish an online presence, like building a website or an e-commerce store, Squarespace has got your back. With Squarespace, you can easily create a stunning website, showcase your work, and connect with your audience without hiring a developer. Squarespace also offers powerful blogging tools for sharing ideas, scheduling content, and integrating with third-party tools through Squarespace extensions. Plus, with Squarespace email campaigns, you can effortlessly gather email subscribers, promote sales, and offer discount codes. They even provide built-in analytics to measure the impact of your email campaigns. So, if you want to give it a try, you can visit squarespace.com/thesecretsoftheuniverse, and if you like it, you can even get a 10% discount off your very first purchase by clicking the link in the description. Amaterasu was discovered by the Telescope Array experiment in Utah. A frequent question is how such a particle is detected. To grasp this, one must first understand the events that occur when a cosmic ray particle collides with the Earth's atmosphere. When these cosmic ray particles, mainly consisting of protons and atomic nuclei, enter the Earth's atmosphere, they trigger a chain of reactions. These particles collide with the nuclei of atmospheric atoms at altitudes ranging from 10 to 20 kilometers above the Earth's surface. Such interactions result in the formation of a variety of secondary particles, leading to the creation of a particle shower. This shower includes pions and kaons, which are inherently unstable and quickly decay into a range of other particles, notably muons, neutrinos, and a cascade of photons, electrons, and positrons. The secondary particle shower generated by cosmic ray collisions in the Earth's atmosphere also includes an electromagnetic cascade. This cascade occurs as photons, electrons, and positrons interact, resulting in a rapidly expanding cone of billions of secondary particles. Detecting these cosmic rays and their resultant secondary particles involves intricate techniques. At the telescope array in Utah, there are two primary methods for detection. The first method employs an array of 60 telescopes strategically positioned to scan the sky in all directions. When cosmic ray showers interact with atmospheric nitrogen, they excite the nitrogen molecules. As these nitrogen molecules return to their unexcited state, they emit fluorescent light, known as Cherenkov radiation, predominantly in the ultraviolet spectrum. The telescopes are thus tasked with detecting these ultraviolet trails as they move through the atmosphere, allowing for the analysis of the shower's longitudinal development. The second approach to detecting cosmic rays involves scattering scintillator detectors across the desert floor. These detectors are roughly the size of ping-pong tables and are made of a plastic material that emits light when charged particles pass through them. The telescope array is equipped with 500 such scintillator detectors strategically placed at intervals of about 3/4 of a mile, or approximately 1.2 kilometers. In a typical particle shower, only some of these detectors are activated. However, the shower caused by Amaterasu was so energetic that it triggered 23 scintillator detectors. This is a significant spread, especially considering the distance between these detectors. By analyzing the timing and the angle at which the shower hits each detector, simulations and computer models are used to trace the shower back to its origin. When scientists tried to determine the origin of Amaterasu, they found something that absolutely blew their minds. Tracing a cosmic ray particle back to its origin is a tricky task, primarily because most of these particles carry an electric charge. This charge means they can be deflected by electric and magnetic fields as they journey through space. However, in the case of Amaterasu, which possessed incredibly high energy, electromagnetic influences should not have significantly changed its path. What could have been a problem is the Greisen-Zatsepin-Kuzmin, or the GZK limit. The GZK limit is like a cosmic speed bump for high-energy particles traveling through space. Imagine cosmic rays as super-fast cars zooming across the universe. As they move, they can run into tiny particles of light from the cosmic microwave background, which is the leftover glow from the Big Bang. If a cosmic ray is moving fast with a lot of energy, it slows down a bit when it hits one of these light particles, like a car hitting a speed bump. This slowing down means there's a limit to how much energy these cosmic rays can have by the time they reach us on Earth. The GZK limit for a proton is 50 exa-electronvolts. It is considered the maximum energy it can maintain over long distances of around 160 million light-years. While many events and objects within this distance can produce cosmic rays, none seem powerful enough to generate particles with such immense energies. Despite their colossal power, supernovae, kilonovae, and even hypernovae fall short in terms of the energy required to produce cosmic rays as energetic as these. Tracing the line of Amaterasu back leads us to the local void. The local void is a vast, seemingly empty region in space adjacent to the local group, which includes our Milky Way galaxy. This expansive area in the universe is intriguing because, in contrast to the dense, star-filled regions we commonly observe, it appears to be largely devoid of galaxies, stars, and other visible matter. But again, the problem is that astronomers couldn't find anything in the local void capable of producing extreme energy cosmic rays. A common question that arises is whether this particle really traveled millions of light years. Could it possibly have originated within the Milky Way, thereby not losing energy in intergalactic space? Astronomers have dismissed the idea of a galactic origin, primarily based on the particle's energy. John Matthews from the Telescope Array Project explains that the Milky Way can generate cosmic ray particles with energies ranging from 0.1 to 10 exa-electronvolts. However, an extraordinarily violent object would be required to produce a particle with hundreds of exa-electronvolts. This object would need to possess incredibly high electric and magnetic fields, as well as a sufficiently large area to contain and accelerate the particle. Currently, there is no known object within the Milky Way capable of generating such a high-energy particle. So, what's really going on? There are 4 potential explanations for the mystery particle, 3 of which might lead to groundbreaking discoveries in physics. The first hypothesis suggests that Amaterasu might be an iron nucleus instead of a proton. If this is true, it would have a lower charge-to-mass ratio, a much higher GZK cutoff, and be more susceptible to deflection by electromagnetic fields in space. This could imply that its origin is not the local void, but entirely elsewhere. The second theory proposes the existence of an unknown, highly violent object, possibly in a galaxy beyond the Milky Way, capable of producing such extreme energy particles. This object might be an exotic star characterized by extraordinary density and electromagnetic fields, undergoing intense disturbances or outbursts. The third possibility considers the existence of a massive yet unidentified particle in the universe. This particle could be decaying, thereby producing particles with energy levels in the thousands of exa-electronvolts. It might even be a dark matter particle, not currently included in the standard model of physics. Lastly, the fourth theory challenges the validity of the GZK cutoff. It suggests that particles with energy levels in the thousands of exa-electronvolts might overcome collisions with the cosmic microwave background radiation through some unknown mechanism. This would allow them to traverse vast distances without losing significant energy. Out of these 4 hypotheses, the possibility of Amaterasu being an iron nucleus or a flaw in the GZK cutoff is more likely. That's because it's not the first time an extreme energy cosmic ray particle has been caught. Dozens of such particles have been detected in the last few decades. Whatever the reason, Amaterasu is an important messenger from the universe, one that has the potential to open doors to new physics. What are your thoughts about it? Recently, the James Webb Space Telescope observed Europa for 10 hours and found a potential life source in the ocean beneath its icy crust. If you missed this episode, be sure to catch up on the exciting discovery.